IceCube Neutrino Observatory, world's weirdest telescope below 10,000 feet of solid ice in Antarctica. You may have heard about an ice telescope's strange, rare, and significant discovery. At first glance, this telescope may appear to be just another piece of equipment for studying the universe. The IceCube Neutrino Observatory in Antarctica is one of our planet's most advanced astronomical observatories. In 2018, this one-of-a-kind telescope that uses neutrinos to explore the farthest reaches of our universe reported the first observation of a high-energy astrophysical neutrino source. Stay tuned until the end to see how the IceCube Neutrino Observatory in Antarctica aids scientists in their research into dark matter and neutrinos. In 2002, University of Wisconsin-Madison researchers launched the IceCube Neutrino Observatory. The telescope employs a unique kind of neutrino detector to determine whether there are any unusual particles out there. The unveiling of the obscured universe has just begun, and neutrinos are set to lead a new era of discovery in astronomy, says Elisa Resconi, a physics professor at TUM and another main analyzer. In this video, we will see how the IceCube Neutrino Observatory is put to use to learn more about the nature of the cosmos. Make sure to keep watching until the end. Before we continue, please give this video a thumbs up and subscribe to this channel for more content. To be notified of new videos, click the bell button. Have you done so already? Let's get this party going. The IceCube Neutrino Observatory is the first of its kind, designated to observe the universe from deep within the ice of the South Pole. The IceCube Collaboration is an international group of scientists in charge of scientific research. The nearly massless neutrino-hunting IceCube telescope covers a cubic kilometer of ice. These high-energy astronomical messengers provide data to investigate the most violent astrophysical sources, such as exploding stars, gamma-ray bursts, and cataclysmic events involving black holes and neutron stars. The Antarctic Neutrino Observatory, which includes the surface array IceTop and the dense infill array deep core, was intended to be a multi-purpose experiment. IceCube collaborators investigate several major physics questions, including the nature of dark matter and the properties of the neutrino itself. IceCube also observes cosmic rays interacting with the Earth's atmosphere, revealing fascinating structures that are currently unknown. The IceCube collaboration comprises approximately 300 physicists from 58 institutions in 14 countries. The international team is in charge of the scientific program, and many collaborators help design and build the detector. The collaboration's exciting new research opens a new window for exploring our universe. The IceCube Neutrino Observatory was primarily funded by the National Science Foundation, NSF, with assistance from partner funding agencies worldwide. The University of Wisconsin-Madison is the lead institution in charge of the detector's maintenance and operation. Each collaborating countries funding agencies support their scientific research efforts. The story of Antarctica's IceCube Neutrino Observatory. Neutrinos are poised to lead a new era of astronomical discovery, according to Elisa Resconi, a professor of physics at TUM and another main analyzer. The unveiling of the obscured universe has just started, she says. Several years ago, NSF launched an ambitious project to broaden our understanding of the universe by combining established capabilities in optical and radio astronomy with new abilities to detect and measure phenomena, such as neutrinos and gravitational waves, Caldwell says. The identification of a neighboring galaxy as a cosmic source of neutrinos by the IceCube Neutrino Observatory is just the beginning of this new and exciting field that promises insights into the undiscovered power of massive black holes and other fundamental properties of the universe. The IceCube Neutrino Observatory is primarily supported and operated by a National Science Foundation grant to the University of Wisconsin-Madison. The IceCube collaboration, which includes over 350 scientists from 58 institutions worldwide, runs a large scientific program that has laid the groundwork for neutrino astronomy. Australia, Belgium, Canada, Denmark, Germany, Italy, Japan, New Zealand, the Republic of Korea, Sweden, Switzerland, Taiwan, the United Kingdom, and the United States are funding IceCube's research efforts, which include critical contributions to detector operation. NSF EPSCoR 2019597 provides additional funding to the IceCube EPSCoR initiative, IEI. Significant funding for the construction of IceCube also came from the National Fund for Scientific Research, FNRS, and FWO, in Belgium, the Federal Ministry of Education and Research, BMBF, and the German Research Foundation, DFG, in Germany, the Knut and Alice Wallenberg Foundation, the Swedish Polar Research Secretariat, and the Swedish Research Council in Sweden, as well as the University of Wisconsin-Madison Research Fund in the US. Why is the IceCube Neutrino Observatory being used? Strong cosmic particle accelerators must exist, as shown by observations of high-energy cosmic rays, protons and atomic nuclei from space, but their nature and location are still unknown. Interstellar magnetic fields after the direction of charged cosmic particles as they travel to Earth, concealing their origins because high-energy photons and neutrinos are not deflected. They could be used to pinpoint the location of the cosmic accelerators. Both travels in straight lines and are produced wherever cosmic rays interact with ambient matter or light, in or near the acceleration sites. Depending on the environment, gamma rays could rapidly lose energy through various processes, including pair production and interactions with lower energy photons. Gamma rays are strongly absorbed over cosmological distances above tera-electron-volt energies by interactions with extragalactic background light and the cosmic microwave background. Because neutrinos are not affected by an intergalactic absorption, they could be used to investigate tera-electron-volt cosmic accelerators. Active galaxies with an active galactic nucleus, AGN, have a very bright central region powered by material accretion onto a supermassive black hole, SMBH. The flow of matter into the SMBH is typically surrounded by an obscuring dusty torus, causing the observable characteristics of AGN to vary depending on the viewing angle from Earth. Seyfert-2 galaxies, for example, are thought to be viewed edge-on, with a line of sight passing directly through the obscuring torus. Sometimes, an AGN can fire a powerful narrow jet of accelerated plasma. If such a jet is oriented close to the line of sight, AGNs have the potential to emit neutrinos. If a plasma jet is present, it may dominate the emission. What is an IceCube neutrino, and how does it work? The IceCube Neutrino Observatory has been operating since 2010 at the Amundsen-Scott South Pole Station in Antarctica. The observatory measures Cherenkov light, ultraviolet and blue photons emitted by charged secondary particles traveling faster than the phase velocity of light in the ice, using 1 cubic kilometer of optically transparent glacial ice as a detection medium. When neutrinos interact with nuclei in or near the instrument, these relativistic, close to the speed of light, secondary particles are produced. 5,160 digital optical modules, DOMs, are installed on 86 vertical cables, strings, spaced 125 meters apart to form a three-dimensional array in the ice. Each DOM keeps track of the number of induced photoelectrons, charges, over time. The IceCube Gen 2 Observatory of the Future. It's already a well-studied object for astronomers, and neutrinos will enable us to see this galaxy in a completely new light. A fresh perspective will undoubtedly yield new insights, says Glauc. According to Ignacio Taboada, a physics professor at Georgia Institute of Technology and the IceCube collaboration spokesperson, these findings significantly improved over a prior study on NGC 1068 published in 2020. Part of this improvement was due to improved techniques, and part was due to a careful update of the detector calibration, Taboada says. the detector operations and calibrations teams work together to improve directional neutrino reconstructions, allowing us to pinpoint NGC 1068 and make this observation precisely. The IceCube collaboration's hard work enabled the resolution of this source through improved techniques and refined calibrations. The improved analysis points the way to superior neutrino observatories, which are already under construction. It's fantastic news for the future of our field, says Mark Kowalski, senior scientist at Deutsches Elektronen Synchrotron in Germany and an IceCube collaborator. It means there will be much to discover with a new generation of more sensitive detectors. The future IceCube Gen 2 Observatory would not only be able to detect many more of these extreme particle accelerators, but would also be able to study them at an even higher energy. It's as if IceCube handed us a treasure map. IceCube is one step closer to answering the century-old question of the origin of cosmic rays with the neutrino measurements of TXS 0506 plus 056. Furthermore, these findings imply that many more similar objects in the universe may have yet to be discovered. The IceCube telescope is one of the most advanced instruments ever constructed, and it has helped scientists learn more about the universe than ever before. The telescope employs a detector of over 5,000 small pieces of ice only a few inches wide. Scientists can gain insight into the universe's biggest mysteries by studying these tiny particles. The video for today has concluded. Remember to thumbs up this video and subscribe to the channel to see more content. Remember to click the bell icon to be notified when new videos are posted. I will say goodbye now and hope to see you in the upcoming video.